Okay, we're going to pick up where we left off on Friday on testing your understanding 2.1. This was a problem using the Heisenberg Uncertainty Principle, and we're given an electron, that the particle is an electron that we're considering, and in part A, we were given the uncertainty in position, delta x, was 8 angstroms. And from the Heisenberg Uncertainty Principle, we can find directly that the uncertainty in momentum, delta p, is greater than or equal to 1.318 times 10 to the minus 25th kilogram meters per second. So we did that on Friday, part A. In part B, we're given that the nominal value of the momentum, I'll call that P nom, the nominal value of the momentum, is given to us as 1.2 times 10 to the minus 23rd kilogram meters per second. And the goal is to find the uncertainty, the corresponding uncertainty in kinetic energy. So we want to find delta E. Now I'm going to take two approaches to this. One I would call the brute force approach. So here's our brute force approach. We observe that the maximum momentum is the nominal momentum plus half of the uncertainty, and that the minimum momentum is our nominal momentum minus half of the uncertainty. So P max is equal to P nom plus delta P over 2, and P min is P nom minus delta P over 2. It's just like we have a number line of momentum. Our nominal is in the middle of the interval, and then the maximum is half of our uncertainty above that, and the minimum is half the uncertainty below that. We know that energy, kinetic energy, is P squared over 2m. So the maximum energy, E max, is our P max squared over 2m, and our minimum kinetic energy, E min, is P min squared over 2m. And we know what P nom and delta P are, so and we know what m is because this is an electron. All those things are known. All right, so we got E max and E min. Everybody have this? So our uncertainty in kinetic energy, delta E, uncertainty in E is E max minus E min. We know what those are in terms of momentum. And we could factor out a 1 over 2m. So it's 1 over 2m times P max squared minus P min squared. This is 1 over 2m times P nom plus delta P over 2 quantity squared minus P nom minus delta P over 2 quantity squared. Now, just FOIL this out, and the P noms, you have a P nom squared here, a P nom squared there, that's going to cancel. There'll be some other cancellation. This delta P over 2 is going to get squared, it's going to cancel. And so some straight algebra, after doing some straight algebra, a few lines maybe, we get delta E, the uncertainty in E, is our nominal momentum, P nom, times delta P over m. Now, P nom is 1.2 times 10 to the minus 23rd kilogram meters per second, as we were given in this part of the problem. Previous problem, we found that delta P, 1.318 times 10 to the minus 25th kilograms meters per second. And m, because this is an electron, is 9.11 times 10 to the minus 31 kilograms. And so we plug in Chegg numbers and we find that delta E is 1.736 times 10 to the minus 18th joules. Converting to electron volts, because we know we have 1.602 times 10 to the minus 19th joules per electron volt, we get 10.8 eV. Of course, this was the key relationship right here, that delta E is equal to P nom times delta P over M. This is our brute force approach. Now let's try a more elegant and hopefully more intuitive approach. Well, if we start here, this is our elegant approach. E we know as P squared over 2M. Well, if we take the derivative of E with respect to P, we get dE dP, little Leibniz notation, 2P over 2M, so this is P over M. And now we treat the derivative here, the numerator and denominator, as separable parts, differentials, and we get dE is equal to P over M times dP. And if we treat these differentials as equal to our uncertainties, so delta dE we replace with delta E and dP we replace with delta P, we get delta E is equal to P over M times delta P, and this is exactly what we found through our brute force approach, so of course we're going to get the same result. So, but much simpler, getting to use our expertise with calculus. Let's take a break and before we do our next problem.